Welcome to Everything Distributed. Today we are going to continue on the discussion for edge computing, but I want to give you a concrete idea what kind of research project and especially the ones in my research group. If you remember what is edge computing, we want to move cloud computing closer to the users or closer to the data. And last time I talked about even if we consider the very simple three-layer architecture, we have cloud server, we have edge servers, and then we have edge devices. There are tons of different research problems that we need to address. And then my research has done some of those. The first one we study the most basic version is a data storage. How do we store data on vehicles? Right now, we have many high-end vehicles. You can imagine that we have very powerful computers on top of each vehicle. And vehicle can be viewed as moving computers. Then how do we utilize that kind of resource? And here data storage is one of them. We propose a concept for micro vehicular cloud that are kind of local and also have a macro vehicular cloud that I can kind of global scale, especially we are targeting at a city scale. Then in this paper, we describe a framework or an architecture for those two concepts to work together so you can store data and you can find data efficiently. And later, we generalize this idea to the concept of a content delivery network. And especially, it's that we use it to help the content network that we are using now. So we call it peer-assisted CDN. And the detailed question that we are addressing is that suppose I have a content, I have a data, how do I know where to store it? And then how do I know how to retrieve the data? Should I go to the CDN server or should I go to the peers? Like in this design, it's a micro vehicular cloud. And then we also propose a space optimal content placement algorithm in our model. And we have also performed some evaluation. And then we also addressing the network aspect. So in many of the design right now, especially for Tesla, it capture each vehicle capture tons of sensor value. For example, it might have a radar reading, or it might have a kind of camera taking pictures, and all of those need to be uploaded to the data center to do some analytics or to train their machine learning model, or to figure out that whether the vehicle needs to be modified to be made more efficient or not. However, if each vehicle only does its a decision to upload certain thing locally, then the bandwidth actually it's a big problem, because that the communication at the data center, it only has a certain amount of a communication that can be supported. And right now, look at outside, how many vehicles do we have? If all of them want to upload at the same time, then very soon the data center cannot handle those amount of data. So we want to minimize the uploading data part. And then here we have a two paper to address slightly different problems. And one very concrete idea is that suppose you look at an intersection, and suppose the intersection is also very busy, and you have different vehicles, each of them kind of slightly look at different directions. So example, this is what vehicle one sees, this is the second vehicle sees, the third and fourth vehicles. And the orientation of camera just adjust or tilt a little bit, and then you can see that there are tons of overlap. But in terms of cloud server, in terms of application, what do we need? We only need to have the final result is a kind of parametric view of that kind of 360-degree thing. We don't really need to have all those redundant information. Okay. So what we propose actually is very simple. We have this tree base, I'll call it hierarchical stitching, meaning that we use a graph stitching to remove the data that we don't really need, and so that we only need to upload the final stitch data. And then actually this is a very old concept called in-network computation. And our contribution is to apply this technique in terms of like vehicles. And then we also propose the idea that what happens if like some vehicle, suppose like vehicle 2 or vehicle 4 has like failed, then how do we recover the original data that we need? And then our paper presents some of the analysis to make sure that this is fault tolerant, to make sure that we can recover from failures. And then we also look at like kind of bigger pictures. Right now we have like tons of like intelligent transportations. For example, like how do we control the vehicle flows? How do we control the traffic lights? And then maybe some of the insurance that will dynamically adjust based on that user behavior, based on how you drive, or like some of the smarter way of charging the money for each vehicle or passage fee, all those kind of things. But the problem is that each system kind of operate on their own. So how do we make sure that all different systems we can like kind of smoothly transition between different systems? And then we propose a blockchain-based system to enable this intelligent transportation system. And high-level idea is that we have those data and then we have those tokens that need to be exchanged. And then we use blockchain or like cross blockchain exchange to achieve this efficient intelligent transportation system. And then the kind of new front that I'm working on is the marriage between edge computing and machine learning. We call it Edgebase ML. And then the first one, we publish a poster at Mobicom, and we also have a kind of fault tolerance version for machine learning that just got accepted in OPODIS. And then we later work on the more complicated algorithm that's still under submission. And then the first one actually won the first place for ACM Mobicom student research in the undergraduate category. So here's a big overview of what we did. For CarML, the idea actually is pretty straightforward. So right now people do distributed computation for machine learning, but they only do that in a kind of one big data center. And then here we propose a way to say that now if you look at those high-end vehicles, actually they have a very powerful chips that can perform that specially designed for machine learning tests. So we design a system for the server to exchange the data with vehicles, and vehicle can do local computation and pass gradient back to the server. Server will update the model and then do this again to make sure that finally the solution or the machine learning model can converge to the optimal points. And then some of the ideas or some of the problem that we address is that, for example, that right now we have edge server or roadside unit, but like on the physical space, where should we place them to maximize the performance of our proposal? And then how do we distribute different data or different computation to each vehicles? And then mobility is also an issue. And what if like some of the vehicles fails? Then we have a solution for those. And then the next one is called Echo CGC. So here we don't look at the whole architecture, we just look at the locally. We have the edge server, we have edge devices, and jointly they want to learn something. And then the communication between the cars and then the edge servers, it's a broadcast channel because it's a wireless medium. Then in this case, the edge server will act like the parameter server. For the machine learning model, you will collect the model, you will update the model and send out the gradient, send out the parameter, and then locally edge server will need to train some data and update the gradient and then send it back to the edge server. And then for the edge device, yes, it only does training, but the new thing that we focus on is that some of the edge server, it might be malicious we call it like Byzantine behavior, meaning that you can use like bogus data to train, or you can lie. Then in this case, what do we need to do? Then we need to have some algorithm to figure out like, okay, who are the bad guys? We somehow need to minimize its impact. And then the news angle that we're dealing with, we propose is that to utilize the broadcast feature and then to design a communication efficient approach to target Byzantine failure. And then we also formally prove that our algorithm can converge to the optimal point. And more importantly, we analytically show that our solution is more efficient in terms of communication complexity than the previous solutions. Okay. Then finally, I want to briefly talk about KRAK, and the idea is kind of similar to Echo CGC, but right now we do get a more realistic edge computing model, which is a three-layer one. We have the cloud server, and we have the edge server, which may be roadside unit or like base station. And we also have like tons of edge devices. And again, some of the devices, they might have suffer from this Byzantine failure. They are malicious. And then the way we do that is that, okay, we have some model, the parameter need to go down, and then each devices will get some real-time local data, and then train some gradient. Once you figure out the gradient, it will send it back to edge server. Edge server will locally do some aggregation after it receives like multiple gradients from nearby edge devices. And once it's done, it will send the aggregate gradient back to the cloud server. And then cloud server finally can update the machine learning model and then begin the new iteration again. And yeah, this framework is very popular, but like in the research before, people have not looked at how to tolerate Byzantine failure in this case. And then we formally prove that our solution can tolerate Byzantine failure and also works in this three-layer edge computing. And we also implement our prototype to train on that different data set to show that it actually converges to the data point. Okay. And then finally, I want to have an acknowledgement of all this great student. Without them, I cannot do all this exciting research. Jamie, Juan, Harry, Angus, Jason, Tommy, Li Huan, Alex, Mark, and Qinzi. And yeah, it's a very exciting work. And then the takeaway, hopefully I convince you that my research is very cool. But if you don't think it's cool, that's fine. Think about something that you want to do, because I think that edge computing will be very, very popular in the next 5 or 10 years. And if you're thinking about doing some application and then utilize it, then edge computing is definitely one of the solutions that you need to think of. And yeah, there are lots of exciting and unexplored problems in edge computing. So yeah, follow the direct research here, and hopefully one day you will find it helpful. Okay, that's all. Thank you.